we're going to take a look at binary and octal and hexadecimal numbers. And the reason that you need to know these is that computers only know ones and zeros. They only know high voltage and low voltage. And so everything that is, at the machine level is just ones and zeros. Those numbers get to be pretty long. And so we use some shortcuts to write the numbers in a way that are easy to go back and forth from binary but aren't quite as long. And those numbers are usually hexadecimal but also octal. Our regular numbers that we're used to are decimal numbers based on base 10. Binary is base 2 because you have 2 digits, 0 and 1. Octal is base 8. You have 8 digits, 0 through 7. And hexadecimal has 16 digits, 0 through F. Once you get to 9, then you need more digits because we're out of the ones that we're used to, and so those use letters. So our decimal numbers, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. You'd think it'd be easy for me to count, but I don't always do a good job. Now for the binary, I'm going to write them as 4 binary digits just because it's easier that way. If you always do 4 digits at a time, then it makes it easy to go back and forth from hexadecimal. It's a way to just kind of keep things ordered. If you have a very long binary number, if you break it up into groups of 4, it'll keep you from making a mistake. So, and no, zeros in front don't change anything. So the binary number for 0 is 0, 0, 0, 0. And then each time we're going to go up by 1. But remember, we only have ones and zeros to work with. So once we get to, so our next one is 0, 0, 0, 1. The next one we can get to is 1, 0. So 2 is 0, 0, 1, 0. Now these places, these have place values, and the place values are powers of 2. This first place is 2 to the 0, which is 1, so that's the 1's place. The second place is 2 to the 1, so that's the 2's place. The third one is 2 squared, or the fourth place. And this one is 2 to the third, or the 8th place. So for the second number, I have a 1 in the 1's place, so this number has a value of 1. The second number, I have a 1 in the 2's place, so this has a value of 2. And I have zeros everywhere else, so it's just 2. 3, the next number I can get to is 1, 1. That has a 1 in the 2's place and a 1 in the 1's place, so that's 2 plus 1, which is 3. Now 4, the next number I can get to, is 0, 1, 0, 0. And so that has a 1 in the 4's place and zeros everywhere else, so it's just 4. And then 0, 1, 0, 1, a 1 in the 1's place, 0 in the 2's place, 1 in the 4's place, that's a 4 plus a 1, which is a 5. 0, 1, 1, 0. 0, 1, 1, 1. That's 7. And so with 3 digits, the biggest number I can make is 7. With 2 digits, the biggest number I can make is 3. So now I get to 8. I'll have a 1 in the 8's place, and then zeros. And so that's 8. And then to get to 9, I'll have a 1 in the 8's place and a 1 in the 1's place. 8 plus 1 is 9. 8 plus 2 is 10. 8 plus 2 plus 1 is 11. 8 plus 4 is 12. 8 plus 4 plus 1 is 13. 8 plus 4 plus 2 is 14. And 8 plus 4 plus 2 plus 1 is 15. So the biggest number you can make with 4 digits is 15, which is 2 to the 4th minus 1. And notice the 7 is 2 to the third minus 1. And 3 is 2 squared minus 1. So the biggest number you can make within digits would be 2 to the n minus 1. Okay, so octal, these numbers can get very long. As you can see, the number 10, well, the number 8 already has 4 digits. And so as you go on, the numbers get longer and longer. So we use other systems that can make these shorter. So octal has the numbers 0 through 7, so those are the same as decimal. 0, 1, 2, 3, 4, 5, 6, 7, but those are all the digits we have. And so the next number, the next biggest number we can get is 1, 0. And then 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, and 1, 6, and 1, 7. Now, just like our place values for binary were 1, 2, 4, 8, our place values for octal are going to be 1, 8, 64, and then 8 to the third. And so if I take this number here, 1, 4, that is going to be 8 to the 1, which is 8, plus 4, which is 12. And so that corresponds to our decimal 12. Now, a lot of times when you write these, you might put in parentheses and put a little 8 to indicate that that is a octal number and not a decimal number, because it looks like 12, but it's not 12, it's 10. And so you can do the same thing with one of these. You could put a B for binary, or you could put a 2 for base 2. And for one of these, if you really want to distinguish it, you could put a D for decimal. You could put a 10 for base 10. Okay, so now let's get to hexadecimal. So hexadecimal is going to have 16 digits. So it turns these binary numbers into 4 digits into just 1 digit. So these numbers are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and now we're out of our regular digits. We've used all 10 of our regular digits, and so once we get to decimal value 10, we go to letters. So A, B, C, D, E, F. Now, you should be able to write these fairly quickly. You should be able to say 12 is 1100 in binary and C in hexadecimal. You should be able to do this pretty quickly, and I'll be honest, with the hexadecimal, sometimes I can't keep them straight and I use my hands. So I know starting with 10, I have letters. And so if I want to get to, say, 13, okay, so then I'll say 10, 11, 12, 13, A, B, C, D. So I know that 13 is D. And vice versa, if say someone wanted to tell me what is E, A, B, C, D, E, 10, 11, 12, 13, 14. So I find my fingers useful for that. Now, you can always look these up, but you're going to want to be able to do it more quickly than that. Now, this makes converting from binary to hexadecimal and hexadecimal to binary very easy. So I'm going to take a binary number, 0, 1, 0, 1, 1, 1, 1, 1, 0, 1, 0, 1. I already used that one. Let's be creative. 1, 1, 0, 1, and 1, 0, 0, 1. Okay, so I broke these up into groups of 4, but this is really just one long number. And if I want to convert that to hexadecimal, I just look and see what do these correspond to. So 0101, 0101 is 5. And if it's a number between 0 and 9, then you can just go ahead and write it because you know it'll be that in hexadecimal. If it's a number bigger than 9, you'll have to use the hexadecimal digit. So 1111, that's 15, that's F. 1101, that's 8 plus 4 is 12, plus 1 is 13, that's 13, 10, 11, 12, 13, A, B, C, D. So that's D. Or you can just look it up on the table. I just wanted to show you what I do. And then 1001, 1001 is 9, and so that's 9. So this number in binary equals 5FD9. Now, let's say I don't give it to you broken up into groups of 4. Then I'm going to start, you start on the right-hand side, and you break it up into groups of 4. So here's my first group of 4. Here's my second group of 4. And if you want to, you can put the zeros on the front to make your last group of 4 so that it just matches what you have in the table. So 1110, that's E. 1010, 1010, that's A. And 0001, that's just 1. So that's converting back and forth between binary and hexadecimal. And going from hexadecimal to binary is just as easy. Let's say I have 2, C, A, 6. So I find the binary for 2, which is 0, 0, 1, 0. The binary for C, C is A, B, C, 10, 11, 12. And so the binary for C, 12, is 8 plus 4. So that's 1, 1, 0, 0. A is 10. That's 8 plus 2. So that's 1, 0, 1, 0. And 6 is 4 plus 2. So that's 0, 1, 1, 0. So that's binary and hexadecimal, and that's how you convert back and forth between them. And those are the easiest conversions. And you can do the same thing for octal. So for octal, it works exactly the same way, only you use groups of 3 instead of groups of 4. So if I had the number 0, 1, 1, 0, 1, 0, 1, 0, and I break that up, let me put another 1 in front, and that's a 1. And I'll break that up into groups of 3 for octal. Oh, I wanted to make this not even, so I'm going to put yet another 1, 1 here. And then we have that, and then I can put a 0 in front. And then this is 2 plus 1 is 3, 4 plus 1 is 5, 4 plus 1 is still 5, and this is 2. So this is the number in octal that corresponds to this number in hexadecimal. So we use a 16 for hexadecimal. And then, of course, to go between octal and binary, you just do the reverse. So if I had 2, 7, 3, and base 8, I'll write these as their binary equivalents. So 0, 1, 0, but using only three digits. So the octal is each digit is 3 digits in binary, and 7 is 1, 1, 1, and 3 is 0, 1, 1. Now, to go between octal and hexadecimal and vice versa, I find it easier to go through binary. So you make it binary, and then you go to hexadecimal. So one last example. So let's say I had 6 to 4 in octal, and I wanted to write it in hexadecimal. Then I'll do binary 1 1 0 0 1 0 1 0 0. So here it is in binary. And then to go to hexadecimal, I need groups of 4. So I'll break this up into groups of 4. And then that becomes 1. And this is 8 plus 1 is 9. And this is 4 in hexadecimal. All right, hope that was helpful.